everyone, today I want to talk about doing the billion row challenge. It's a programming challenge where you get a text file with a billion lines, about 13 gigabytes total. Every line contains a weather station and a temperature, like Hamburg 12.3. The goal is to print for every station the minimum temperature, the average temperature, and the maximum temperature, sorted alphabetically. I first found this challenge through some streamers doing it, and turns out there's a website for it, onebrc.dev. It has language cards for whatever language you want to attempt this in, so Java, Go, and of course I clicked the Rust card because obviously I was going to try this in Rust. And nothing happened. The link was broken. Turns out all of the links on the site were broken, including the link to the GitHub repo, so I was kind of like, what is going on? After a bit of digging, I found the original repo by Gunnar Morling and realized that the 1 billion row challenge was originally a January 2024 competition. The leaderboard is final and new submissions are closed. So yeah, I was a little late, just a little. But even though the contest is over, it's still a really good performance engineering exercise, so I decided to do it anyways. The next issue, though, since the website no longer really worked that well, was getting hold of the data. There was not just a 13 gigabyte file sitting there to download. The input was generated on demand. The original repo has a CSV of weather stations, but that CSV is not the measurements file. It's more like source data, station names, and average temperatures. The actual billion rows are generated by repeatedly picking up a station and generating a temperature around that station's average. Also, the CSV in the repo is a larger expanded list used by a later generator, but the original canonical challenge used a fixed set of 413 real stations baked into a Java generator, because yeah, the original challenge seems to have been in Java. I wanted my version to match the original challenge setup, so I ported that 413 station generator over to Rust. That let me generate files at any size, 1,000 rows for testing, 100 million rows for benchmarks, or the full 1 billion rows, which comes out to around 13 gigs. Once I finally had the data, I gave myself one extra rule: safe Rust only. No unsafe, no external crates, no C foreign function interface. Just stable Rust and the standard library. I knew that would rule out some of the fastest tricks that people use though, especially memory mapping and explicit SIMD, but I wanted to see how far I could get while keeping the whole thing completely safe. 'Cause yeah, safety first. So the program opens the measurements file, figures out how many hardware threads the machine has, and chops the file into 16 megabyte chunks. Those chunks are handed out to worker threads through a shared atomic counter. So every thread keeps grabbing more work until the whole file is done. Each chunk has to be adjusted so that it starts and ends on a complete data line. A chunk boundary almost always lands in the middle of something, and if it cut through Hamburg 12.3, one thread might see Ham while another sees Berg 12.3. That would obviously break the parser. So before processing, the boundaries are nudged forward to the next new line. Each worker thread streams its assigned chunks in 2 megabyte blocks using read@. That matters because read@, lets a thread read from a specific byte offset without moving the shared file cursor. So multiple threads can read different parts of the same file without constantly fighting over one global position. Inside each worker, the job is to parse a line, find the station name, parse the temperature, and update that station's stats. Every worker has its own hash table, so there's no lock around every row. If the line is Hamburg 12.3, the parser finds the semicolon, treats Hamburg as the key, turns 12.3 into the integer 123, and then updates Hamburg's minimum, maximum, running sum, and count. That integer detail is important. The input looks like floating point numbers, but I never actually store them as floats. Since every temperature has exactly one decimal place, I store everything as tenths of a degree. So 12.3 becomes 123, negative 4.8 becomes negative 48, and 0.5 becomes 5. That keeps the hot loop in integer arithmetic, which is faster and exact. After the workers finish, the program merges the per thread tables into one final table. Then it collects the station entries, sorts them alphabetically by name, and formats the integer tenths back into 1 decimal place strings and writes the final output in the canonical 1BRC format, which is one line of station equals min mean max. So the first big improvement here was parallelism. The file is independent line by line, so there's no reason why one core should do all of the work. But the important detail is how the work was split up. So my laptop has an Intel i3-121.5U, which is not 8 equal cores. It has 2 faster performance cores and then 4 slower efficiency cores. If I gave each thread 1 equal slice of the file, the performance cores would finish early and sit there waiting for the efficiency cores. So instead, I split the file into many small chunks and let each thread grab the next chunk whenever it finishes. The fast cores naturally do more work, and the efficiency cores still contribute, and the whole CPU stays busier. There was also a small optimization around those chunk boundaries. At first, I calculated the line align boundary whenever a worker grabbed a chunk, but the neighboring chunks share boundaries, so I was doing some of the same little boundary reads more than once. I changed it to compute all the line align boundaries exactly once up front before the worker threads start. Then I looked at the hot loop, the part that runs 1 billion times. My first parser scanned each line twice. It found the new line, then went back and found the semicolon, but the temperature format is fixed. Optional minus sign, 1 or 2 digits, a decimal point, and 1 digit after it. So once I find the semicolon, I can parse the temperature and know exactly where the line ends. That turns 2 scans into 1 fused pass. The next bottleneck was finding the semicolon itself. A normal parser checks 1 byte at a time. Is this byte semicolon? Is this byte a semicolon? Is this byte a semicolon? What about this byte? So I replaced that with an SWAR trick, which stands for SIMD within a register. The code loads 8 bytes into one 64-bit integer and then uses a few bitwise operations to ask, does any byte in this word equal semicolon? It's not real SIMD, yet it doesn't require unsafe code, but it still moves through the station name 8 bytes at a time instead of 1. Temperature parsing was another rabbit hole. A simple parser has branches like, is this number negative? Is there 1 digit before the dot or 2? Where is the decimal point? Across a billion rows, those little branches do matter. The CPU keeps trying to predict them, and then when it guesses wrong, it actually has to throw away work. So I switched to a branchless parser. It reads the temperature bytes as one word, finds the decimal point with bit operations, extracts the digits, handles the sign, and combines the result with a multiply. The output is still just an integer number of tenths, so the hot loop never touches floating point. I also made the final average calculation integer only. The average has to be rounded to 1 decimal place, which matches Java math.round behavior from the original challenge. Instead of converting the sum and count to floating point, I compute the rounded result directly with integer arithmetic, so parsing the input to printing the final answer, the solution avoids floating point math completely. I also noticed that I was clearing a buffer before reading into it, but reading from the file immediately overwrites that memory anyways, so I was writing a bunch of zeros just to throw them away. Reusing 1 buffer per thread without repeatedly clearing it removed the pile of pointless memory writes. Station lookup got optimized too. Rust standard hash map is general purpose, but I know a lot about this input. There are at most 10,000 unique stations, and every thread is only updating its own table. So I used a fixed size open addressing table. Station names are copied once into a byte arena, and each row updates the min, max, sum, and count in place. The min and max updates are branchless too. Instead of if, val, then current min style branches, they use Rust's built-in min-max methods, which actually compile down to conditional moves. Same idea as the temperature parser. Keep the CPU from having to guess. The station name is hashed 8 bytes at a time, and then Fibonacci hashing maps that hash into a bucket. The golden ratio constant helps spread keys evenly across the table without doing expensive division. I also trimmed the entry struct itself. Originally, each slot cached the station's hash alongside the min, max, sum, and count. Dropping that cached hash and shrinking the row counter from 64 bits to 32 bits, which is still plenty since the billion rows fit easily in a 32-bit number, that brought the entry count down to 24 bytes. Smaller entries mean that more of them fit in a cache line, so as the station count grows towards the 10,000 limit, the table stays much friendlier to the CPU's caches. Of course, fast is not great if it's wrong, so I had to check correctness a few ways. I compared the output against a simple reference implementation. I tested the branchless parser against every valid temperature from negative 99.9 to positive 99.9. And I checked the billion row run to make sure the expected stations and averages lined up. So yeah, how fast did it end up? On my laptop with an Intel i3-121/5U, 2 performance cores, 4 efficiency cores, 7.4 gigabytes of RAM, and an NVMe SSD, the full billion row file finishes in about 10 seconds, which I was actually kind of disappointed in because I had seen people report 1 or 2 second runs. But then I realized that those numbers assume something that my laptop simply does not have, which is enough RAM to cache the whole 13 gigabyte file. My machine has 7.4 gigs of RAM. Yeah, we're in Ramageddon. So the file is 13 gigs. I cannot fit it in the page cache. Running the benchmark again does not make it much faster because by the time the operating system reaches the end of the file, the beginning has already been evicted. So every run has to stream almost the whole thing from SSD all over again. And the math lines up almost perfectly. 13 gigabytes in about 10 seconds is 1.3 gigabytes per second, which is basically the read speed of my drive. At that point, the program is not really waiting on the CPU, it's waiting on that storage. So to separate the CPU time from disk time, I also benchmarked a smaller file that does fit into my memory. There, the parser does about 200 million rows per second. Scaled to a billion rows, that's about 5 seconds of parsing work. But on the full dataset, the SSD takes about 10 seconds to deliver the bytes, and the parsing work happens underneath that I/O. So on this machine, more hot loop optimization would not really move the full billion row number. The next speed up would have to come from faster reads, either a faster drive or enough RAM to keep the whole file cached. And that's why I think the 1 billion row challenge is such a good project. The problem fits in one sentence, but every optimization teaches you something about how computers actually work. As always, the code for the project is on my GitHub if you'd like to check it out. And thanks for watching. Until next time, bye!